Assalamu alaikum. In last session, we discussed exercise 6.2 arithmetic series from question number 1 to 8, and now we are going to discuss question number 8 part 2. In question so on. In question number 8, we are going to find the number of terms because question is how many terms of each of the series. The series is given -9, -6, -3 up to so on must be taken to amount to 66. Explain the double answer. Okay. The question is how many terms of each of the series of the series the series is -9, -6, -3 and up to so on must be taken to amount must be taken to amount to 66. Explain the double answer. Explain the double answer. Okay, solution is okay. The sequence is as given -9, -6, -3 up to so on. So here the first term, that means a is equal to -9, and the common difference d you can find by subtracting second term with first term. So we get the common difference is 3. You know that the sum of the series is given as Sn is equal to n upon 2, 2a plus n minus 1 of d. So now put the values as given in the question, and the sum of the n series is 66. Here Sn is 66. So we put the values of Sn n upon 2. The value of a is -9 plus n minus 1 and d is 3. Okay. So 2 the denominator में डिवाइड हो रहा है तो पेरिटी के अदर साइड पे जाके मल्टीप्लाई होगा, तो 2 is multiplied by 66 is equal to n -19 plus 3n minus 3. 132 is equal to n minus 18 and minus 3. So here minus 90 and minus 3 is equal to minus 21 plus 3n. 132 is equal to minus 21n plus 3n square. So we get quadratic equation, and we have to find the value of n with the help of quadratic formula or factorization method. So 3n square minus 21n minus 132 is equal to 0 is a quadratic equation. Okay, we can take common 3 from this equation. So 3 is a common, n square minus 7n minus 44 is equal to n. So 3 after the equality, other side of equality will be 0. N square minus 7n minus 144 is equal to 0. Okay, we can break this middle term as minus 11n plus 4n. So we get the minus 7. Okay. Here we can take common n minus 11 plus 4, n minus 4, 11s are 44. So n plus 4 and n minus 11 is equal to 0. So here either n plus 4 is equal to 0 or n minus 11 is equal to 0. From here we get n is equals to minus 4 and n is equals to 11. So the number of term cannot be negative. So we can not take this value n is equals to minus 4. We take n is equals to 11. So the total number of term is total number of terms is 11. The number of term cannot be negative integer, so we cannot take n is equals to minus 4. Now the question number 9 is given as question number 9. Find the sum of all natural numbers between 250 and 1000, which are exactly divisible by 7. Find the sum of all natural numbers between 250 and 1000, which are exactly divisible by 7. Okay. So first we find the numbers between 250 to 100 which are divisible by 7. So numbers divisible by 7 between 250 and 1000 are 252, 259, 266 and up to so on till 994. These are the number between 250 and 1000 which are exactly divisible by 7. So this is the arithmetic sequence. Here A is equals to first term, that is 252, and the common difference is 259 minus 252, which is 7. And the last term or TL is equal to 994. We have to find the sum of the natural numbers between 250 to 100. We know that nth term is equal to a plus n minus 1 of d, and the last term is 994 is equal to a is first term, that is 252 plus n minus 1, and the difference is 7. 994 is equal to 252 plus 7n minus 7. 994 minus 252 is equal to 7n minus 7. 994 minus 252 is equal to 742. 742 plus 7 is equal to 7n. 749 is equal to 7n, and 749 upon 7 is equal to n. So here the number of term is 107. N is number 107. Now we have to find the sum of the n term Sn. The formula of sum of the n term is equals to n upon 2 twice of a plus n minus 1 of d. N is 107. 107 upon 2. A is 252 plus 107 minus 1, and the difference is 7. S107 is equal to 107 upon 2, and the 252 in 2's are 504 plus 106 into 7 is equal to 107 upon 2. 504 plus 106 multiplied by 7 is equal to 742. S107 is equal to 107 upon 2, and 504 plus 742 is equal to 1246. Okay, S107 is equal to 107 and 623. So S107 is equal to 107 multiplied by 623 is 1. This is the sum of 107 term. Is the required answer. Similarly, in question number 10, the question is find the sum of all natural numbers between 1 and 100 which are not exactly divisible by 7. Question number 10 is like question number 9. You can do easily by yourself. Look at question number 11. Question number 11. In question number 11, find the sum of an arithmetic progression of 17 terms whose middle term is 5. Find the sum of an arithmetic progression of 17 terms whose middle term is 5. Middle term is 5 and we are given as the sum of arithmetic progression of 17 terms, and the 17 is an odd number. So middle term for odd number is given as n plus 1 upon 2. This is the formula of middle term. So here n is 17 plus 1 upon 2 is equal to 9. 9 term. Okay, this is middle term. We know that the nth term formula of nth term is given as Tn is equal to a plus n minus 1 of d. Here n is equal to 9. So T9 is equal to a plus 9 minus 1 of d. So T9 is equal to a plus 8d. And we know that the middle term T9 is given as 5. So we put here the value of middle term, that is 5. So 5 is equal to a plus 8d. This we say our equation number 1. As we know, the sum of the nth term Sn is equal to n upon 2 plus n upon 2, 2a plus n minus 1 of d. As we find n is equal to 17, because in the question, find the sum of an arithmetic progression of 17 terms. So n is 17. We put the all values given in the formula. S17 is equal to 17 upon 2. 2a plus 17 minus 1 of d. S17 is equal to 17 upon d, twice of a plus 16d. 17 upon 2, we can take 2 as a common. So here a plus 8d is left. Okay. S17 is equal to 2 will be cancelled with this 2, 17, and the value of a plus d is equal to 5 in equation number 1 implies. Equation number 1 implies a plus 8d is equal to 5. So we put the value of a plus d is equal to 5. So we can write in the place of a plus d 5. S17, the sum of the 17 terms is equal to 85 is the required answer. Is the sum of an arithmetic progression of 17 terms whose middle term is 5. Now in question number 12, the question is show that the sum of the first and even natural numbers is equal to 1 plus 1 upon n times the sum of the first and odd natural numbers. So, okay. Okay. Show that the sum of first even natural numbers is equal to 1 plus 1 upon n times the sum of the first and odd natural numbers. Solution. The natural numbers are the natural numbers are 1, 2, 3, 4, 5 up to so on. And even natural numbers are 2, 4, 6, 8 up to so on. First we find the nth term. Tn is equals to a plus n minus 1 of d. And here in the even natural numbers, the sequence of even natural number, here a is equal to the first term which is 2 and d is the difference. Second term minus first term, 4 minus 2 is equal to 2. We put the value in the nth term formula. Tn is equals to a is 2 plus n minus 1 and the common difference is 2. So Tn is equals to 2 plus 2n minus 2. The last nth term is equal to 2n. So even natural numbers are 2, 4, 6 up to so on to n. And the sum of n even natural number is given by the formula of sum of n terms is given as Sn is equal to n upon 2, 2a plus n minus 1 of d. So Sn is equal to n upon 2, 2a is 2 plus n minus 1 and d is also 2. Sn is equal to n upon 2, 4 plus 2n minus 2. So 2 plus 2n. We can take 2 as a common. So n plus 1, 2 से 2 cancel. So the sum of n terms is n of n plus 1. This is the sum of n natural even numbers. This is the sum of n natural even numbers. Now the odd natural numbers is given as odd numbers are 1, 3, 5, 7, 9 and up to so on. Here a is equal to first term, that is 1, and the d is 3 minus 1 is equal to 2. Sum of n odd natural numbers number is given by Sn is equal to n upon 2, 2a plus n minus 1 of d. So Sn is equal to n upon 2, a is 1 plus n minus 1 and the difference, common difference is 2, n upon 2, 2 plus 2n minus 2. Minus 2 plus 2 will be cancelled and 2n. So the sum of the n odd natural numbers are n square. This we say the sum of first odd natural numbers. According to given condition, in the question, show that the sum of first n even natural number is equal to 1 plus 1 upon 1 upon n times the sum of the first n odd natural numbers. This is the first n odd natural number, sum of first odd natural numbers, and we have to show the sum of the first n even natural number is equal to 1 plus 1 upon n times of first odd natural numbers. Now this is n square is the sum of first odd natural numbers. 1 plus 1 over n times is equal to the sum of the n even natural numbers. Implies we take LCM as n plus 1. Square would cancel 1 n. we get n of n plus 1, and n plus 1 is equal to the sum of n even natural numbers. Even natural numbers. So we have to prove this. Okay. In question number 13, the question is if the sum of p terms of an arithmetic progression is the same as that of the sum of q terms, show that the sum of p plus qa term is 0. Okay. If the sum of p terms of an arithmetic progression is the same as that of the sum of q terms, show that the sum of p plus q terms is 0. Okay. Let a be the first term and d be the common difference so sum of p terms of an arithmetic progression is given by we know that the sum of n term is equals to n upon 2 2a plus n minus 1 of d. So the sum of p term is equal to st is equals to p upon 2 2a plus p minus 1 of d. So we can write sum of p term as p upon 2 2a plus p into d minus d. This we say equation number 1, and similarly the sum of q term terms is given as sq is equal to q upon 2 2a plus q minus 1 of d. So we can write sq is equal to q upon 2 2a plus q into d minus d, and we say this equation number 2. In the question is if the sum of p terms of an arithmetic progression is same as that of the sum of q terms, according to given condition in the question, according to given condition, The sum of the P term is equal to the sum of the Q term. That means SP is equal to SQ. So the value of SP and SQ as equation number 1 and 2, we have SP is equal to P upon 2, 2A plus P into D minus D, and SQ is equal to Q upon 2, 2A plus Q into D minus D. 2 will be cancelled with this 2, and we get 2AP plus P square D minus P into D. Here 2AQ plus Q square into D minus QD. 2AP minus 2AQ, and this is Q square D minus QD minus P square D plus P into D. Because we find the value of D from this expression, we take 2A as a common, we get P minus D, P minus Q. And after that, we can take D as a common. So Q square minus Q minus P square plus P. So 2A P minus Q upon Q square minus Q minus P square plus P is equal to D. This is the value of D. We say this is our equation number 3. And now we have to show that the sum of P plus Q term is 0. So sum of P plus Q term is given by SP plus Q is equal to P plus Q upon 2. We are putting in the formula of Sn is equal to n upon 2 plus 2A plus n minus 1 of D. So 2A plus n is P plus Q, n minus 1, so P plus Q minus 1 of D. We say this is so we put the value of D in this equation, P plus Q upon 2 plus 2A plus P plus Q minus 1, and the value of D is in equation number 3 implies the value of D is 2A P minus Q upon Q square minus Q minus P square plus P. This is the value of D. Let me find the first given condition. SP is equal to SQ. Okay. SP plus Q is equal to P plus Q upon 2. We take 2A as a common. So here 1 plus p plus q minus 1 p minus q upon q square minus q plus p square minus p. 2 will be cancelled. Sp plus q is equal to p plus q into a, and we take LCM as q square minus q plus p square minus p. So here q square minus q plus p square minus p plus p plus q minus 1 into p minus q. Sp plus q is equal to ap plus q upon q square minus q plus p square minus p. Here q square minus q plus p square minus p plus p multiplied by p square minus pq plus pq minus q square minus p minus minus plus q plus q square with cancel with minus q square. Okay, so minus p square is cancelled with plus p square, minus pq with plus pq. Sorry, this is our plus p. So plus p plus p cancel with minus p, and minus q cancel with plus q. So this all term will become 0. So sum of p plus q terms is equals to a p plus q, a of p plus q upon q square minus q minus p square plus p. This is plus p and this is minus q. And this term will become 0. So the all term and the sum of p plus q term will be 0. This is what we have to show. So sum of p plus q term is equal to 0. Hence proved.